Good afternoon, everyone. I will now present my work on a generic post-hoc explanation model for recommender systems. This is a joint work between Calidea Company and the University of Tours. Recommender systems are nowadays ubiquitous and valuable tools to end users and decision makers, as seen by the illustration. They often present a simple result, such as a few items, but the underlying mechanism is generally hidden and complex. For example, in the case of matrix factorization models. Explaining this process to the user in simple terms, using concepts that he or she knows, represents a challenging task that can improve trust in the system. So how was this problem tackled in the literature until now? We can first differentiate between intrinsic and external explanation models. Intrinsic methods change the internals of the recommender system to build an explanation in parallel with the recommendation. But it may alter the accuracy of the recommendations. Whereas external post-hoc explains the output of a recommender system afterwards. Most of the time, they are related to a specific recommender system. However, Lime RS is an adaptation of Lime that adapts to any recommender systems. Our objective is to achieve the same flexibility while improving its performance. Most of those methods take root in the Lime algorithm because of its popularity among businesses and its effectiveness. Lime produces an explanation as a weighted set of binary interpretable features. Lime goes through several steps that the schema on the left illustrates. First, it does a projection of the explained instance into interpretable feature space. Secondly, it builds a neighborhood by binary perturbation. Third, for each projection, it retrieves the predicted class. Fourth and last, it learns the explanation as a linear regression model. However, this is a classification-based method. It's not directly adaptable in the recommendation context. We don't have a traditional instance feature representation. There is no clear definition of an explanation instance. We don't know how to deal with perturbated points in the special case of matrix factorization, and we also need a proper definition of locality around the explanation instance. So our first contribution is to define an explanation instance as a tuple, user item prediction of the black box rating. In this context, interpretable features are the set of all other items not involved in the explanation instance. This is particularly useful in the context of recommender system, as we must ensure that users receive an explanation that they are able to understand. Similar to Lime, we formalize our explanation problem as an optimization problem, where we search for a linear combination of interpretable features that minimizes a prediction error on the black box output. However, we consider real value interpretable features instead of binary. So our problem boils down to a linear regression with a lasso regularization. We then define a neighborhood around the explanation instance in three fashions. First, we use a continuous perturbation mechanism as a Gaussian noise over values of the user tuple TU. And we introduce an out-of-sample prediction for matrix factorization to represent perturbated points in the original space. They are represented with triangles in the schema. And secondly, our other neighbors definition is done with a k-means clustering of users on a 3-dimensional UMAP projection. They are represented with a dot circle on the schema. This figure on the left presents the mean average error on 3 distinct scenarios: randomly selected items, top recommended items, and least recommended items. We call it flop. And here lower is better. We can observe on the figure on the left that among all our approaches, LIRP performs best. LIRP has a significantly lower average rating error for top recommended items, and in this case the mean average error is equal to 0.89 versus Lime RS that has a mean average error of 1.59. One has to note also that there are no statistically significant differences between Lime RS and LIRP. One difficulty in evaluating explanation models is the lack of ground truth. To avoid this problem, we propose 2 innovative ways to produce an artificial ground truth. First, a single white box, where we replace the actual black box by a predetermined linear model with known coefficients. We want to estimate to which extent our approach is able to find the correct explanation among all possible. Second, a double white box, where 2 distinct linear models are used depending on distance to the explanation instance. And here we want to estimate to which extent our approach is able to find the correct local explanation. In this slide are displayed the results for the single white box experiment in terms of normalized discounted cumulative gain and in terms of item relevance. Our 3 methods perform better than a random baseline, while a Lime RS is not able to retrieve any relevant items due to its perturbation mechanism. LIRP produced the overall best result with a 0.21 of relevance. Again, in the double white box experiments, LIRP comes on top with a 0.328 relevance against 0.03 relevance for Lime RS. The overall domination of LIRP can be explained by its use of a tight neighborhood relying on Gaussian perturbations. Meanwhile, LIRC is penalized by its complex projection and clustering mechanism that is not precise enough in capturing locality. In conclusion, we proposed a model agnostic algorithm to explain recommendations that outperform its only direct competitor, Lime RS. We also achieve better scaling on larger datasets such as movie length 20 millions. But can we do better? And I think that we did. In fact, at the moment we are trying to improve our work with 3 main ideas in mind. The first one is to modify our objective function with a new pairwise approach. Indeed, in a recommendation context, the black box is a scorer, so it induces pair of preferences between points. We can then use a 1-layer rank net without bias to solve that problem. And so far, by doing that, we have achieved promising results. We had a 0.8 of relevance for LIRP pairwise on the single white box experiment, which is almost 3 times better of what we currently have. Then we plan also on improving the locality of LRC by modifying the way we get neighbors points around the explain instance. And finally, test our framework with other recommender systems, so to empirically prove that our model is indeed an agnostic one. Thank you for your attention, and feel free to contact us for any question or leave us a message in the comment section below.